So far, we have dealt with linear or translational motion. Linear and translational mean the same thing. I think I haven't used the word translational before, but it's just, there's another term. Occasionally you run across it. Translational motion is the same as linear motion. The center of mass moves, or some object moves from one point to another. And we have terms, displacement, I guess, position, displacement, velocity, acceleration, time, mass, force, momentum. Now for each of these, there's a rotational analog. So we're now going to get into, in chapter 8, rotational or angular motion. We can now have things spin. So here, position, I'm just going to use x, s, r. There are several things that can use. Displacement, delta x. Velocity is v. That's not mine. All right. Acceleration, time, mass, force, momentum. So there's a rotational analog of it. So instead of position, you're dealing with basically how things rotate, and so the analog is angle. Now, when you start getting into the rotational stuff, this is when physicists decide to start using Greek letters a lot. So the symbol is usually theta or phi. Those are the two most common ones, theta or phi. So this is theta, phi.
How do you draw theta?
It's basically like an oval yin yang. Lowercase for the purists out there. Although there's nothing inherently wrong with uppercase for it. Displacement, angular displacement. Or generally they say through what angle does it rotate or something like that. That's another wording for it. And it's just the delta in front of whatever you're using for angle. So delta theta, delta phi, delta whatever letter you're using. You can pretty much use almost any Greek letter for angle other than the ones that I'm going to list. Don't use pi ever for a variable, for an angle. Never, ever. Like one astrophysics textbook would use pi as an angle instead of the actual number pi. It took me a half hour to realize why pi was there.
What we found out?
What was that?
What we found out?
I did eventually figure it out. The only place I've ever seen pi used as a variable. All right, velocity, angular velocity. Now, if you said rotational velocity, yes, physicists would know what you're talking about, and there's nothing wrong with it. Out of tradition, typically the word angular is used there. So whether it's angular or rotational usually depends upon habit or what your mood is at that time. But angular velocity, the symbol used for that is a lowercase omega, which looks like a W with curves. This is an omega. Again, lowercase.
So do they all have angular in front of them for that?
They will not all have angular in front of them.
Okay.
All right, Anyone take a guess what the rotational or angular analog of acceleration is?
Angular acceleration.
Absolutely. Anyone want to take a shot at the symbol?
Alpha?
Yes, it is. The angular analog of time.
Is it just time?
It is indeed just time. Time doesn't care if something's spinning or moving in a straight line. That's still t. All right, so mass does have an angular analog to it. It has two names to it. Sometimes it's called rotational inertia. I think that's what your textbook does, and I've seen it in more textbooks over the past 10 years. Rotational inertia. Or moment of inertia. In engineering, if you see the term moment, that is generally in reference to something with a twisting involved. So that's the analog of mass. The symbol, they get away from the Greek letters in this one, the symbol is a capital I. I will tend to call it moment of inertia just out of decades of habit. So be able to translate in your head, rotational inertia, moment of inertia, the same thing. The rotational equivalent of force is called torque. The symbol, back to the Greek letters, is a tau. And in what used to be my most obscure reference, I actually had a student who knew the reference. Shocking. This is obscure even when it was current. You may also refer to torque as G2 Kumbuka. Now, most likely, no one will understand that reference except for people who've had me before, and that student from a couple years ago who actually had me, but he knew it beforehand, because he listened to his father. I think there was an important lesson there. And I'm not going to explain it. All right, and then momentum, angular momentum. And the symbol for that is a capital L. Sometimes a lowercase l, but capital L for what we're doing. Now, we have said that we're going to double the number of formulas, so at least I want to get one before we lose Brianna. Or do I need to do this first? As well as making for the traditional exciting video. There's a quiz that I'll give you next week. All right, so doubling the number of formulas. So let's just pick one of the formulas that we have used in the past. F equals ma. To get the new formula, we just go to the analog. What is the analogy or the analog for force?
Have a good day.
Thank you. Moment of inertia?
Lined up wrong there.
I ain't got that right. Torque.
Yeah.
I did that.
Torque equals the analog of mass.
Moment of inertia.
There we go. And analog of acceleration.
Alpha?
Yeah. So Newton's second law for rotating units. Take another equation. I know that I have a PowerPoint on this one. I might have mentioned it briefly in class at some point, but another equation delta x is equal to VIT plus 1/2 AT squared. What would be the rotational version of this?
Change of theta equals omega initial time plus 1/2 alpha t squared.
Yep. Let's do momentum. I know that P is equal to mv. What would be the rotational? What's the formula for rotational? Angular momentum.
L equals I
Is that W, omega?
Okay. Kinetic energy, as you all know, 1/2 mv squared. What about rotational kinetic?
No.
1/2 I omega squared.
All right. I want to comment on this last one. Now, we could keep going, but that's fine for what I'm trying to do. When I asked you to memorize 1/2 mv squared, I did that because that formula doesn't change. It's 1/2 mv squared. If you're working on your Nobel Prize winning work or you're taking physics 110, it's still 1/2 mv squared. But suddenly we have a different formula here. So how do I reconcile the fact that that doesn't change with the fact that there looks like a due formula? And part of that we'll definitely go into next week. But this deals with, suppose you have an object where not everything's traveling at the same speed. As in when something rotates. If I shut the door, the parts of the door closer to the hinge are not moving as fast as the parts farther away. And so that gets taken into account. I'm going to stop it there. I have, so there's, I guess, no, I should stop the video. Test corrections, I did send out